So our next speaker is Supreet Venkatesh. He's a staff system architect at ARM, and he'll be talking to us today about Server Base Manageability Guide for SBSA compliant ARM servers.
Thanks, Jonathan. Hi, welcome to the session on Server Base Manageability Guide for SBSA compliant ARM servers. I'm Supreet Venkatesh. I work as a system architect at ARM. I'm also part of Open BMC TSC, as well as I represent ARM at DMTF work group, PMCI work group, as well as I am the maintainer of UFI SCT and represent ARM at UFI forum as well. So the agenda for today is we'll discuss what was the need or why the need for a server-based manageability guide for server-based system architecture, compliant ARM servers. And we'll briefly go through the history of what other specifications that existed. And we will introduce you to the server-based manageability guide as well. Then we'll discuss, we have a motto at ARM that we don't write specification without validation. So we'll explain how we will upstream features or reference implementations using OpenBMC. And then finally, we have a roadmap or a plan to accomplish that. I'll discuss that with you. And finally, the actions that we need to take in order for us to be successful. Okay, so why do we need server-based manageability guide? It's basically because without it, ARM ecosystem partners would have point solutions that would lead to fragmentation. So our goal is to kind of standardize the common manageability capabilities with scope for flexible customization, which can add value to the end user. The main goal or the objective of this specification is to leverage the industry standard specifications, including Redfish, PLDM, MCDP, as well as IPMI, as well as leverage the hardware management specifications and designs as defined by the Open Compute project. So ARM is pretty new into the server market. So the first thing ARM came up with is a server-based system architecture specification. It basically defines the hardware requirements for the platform to be called as a ARM server. It standardizes the key aspects of the system architecture and as well as the processor elements. This is a public specification and it's available in the ARM website. Once we have the hardware requirements, the next logical step for us was to define the software requirements for the platform to be called as a aarch64 server. So server-based boot requirements kind of caters to it. It basically defines the boot and runtime services expected by a enterprise platform operating system or hypervisor to boot out of the box. So this is loosely based on UFI, SMBAS, and ISCPI specifications. So there are several different levels of compliances on server-based system architecture. So in order to validate the compliance levels, we do have architecture compliance suite. which has tests which test against SBSA and SBBR specifications. This is open source and is available in GitHub. This is built on top of Linux UEFI validation operating system. It basically has SBBR set of tests, which is part of UEFI self-certification tests, as well as there is a SBSA component, which is a UEFI shell application, which runs and which tests the SBSA portion of the requirements. Other than the firmware side of requirements, the interface between the operating system and the firmware, to test that, there is a set of test suites, SBBR, which is part of firmware test suite, which kind of is also open source. And there is a SBSA test suite which is built into the Linux UEFI validation operating system, and that tests the SBSA specification. So this was a brief history of what specification we had in the server space. So the next logical step for us is to kind of come up with a manageability specification, which basically defines what sort of manageability features that needs to be implemented in a platform that should be called as ARM server. So this is currently under development in conjunction with partners across the industry. SVMG is being developed in ARM server AC community. So it's all public process. It's similar to any other standard bodies. If there is an engineering change request that needs to be raised, any one of you can raise that against the Mantis, which we have. To get the access to the Mantis database, you can send an email to ARM server AC, and we could create an account for you. So with SBMG, we have 3 different compliance levels, basically M0, M1, and M2. These compliance levels are based on, so our use case is typically you are used to kind of having an ARM-based BMC communicating with an x86-based server or a power server. So in our case, it's ARM-based BMC communicating with an ARM-based host or an SOC. So currently, the criteria for the compliance levels are the interfaces that are there between the SOC-based host and the BMC, and then the interface that is there between the BMC and the platform elements, and what is the interface to the BMC itself. And the interface between the BMC and the IO devices, basically the network controller, storage controller, or any other IO devices that you may have. So currently we are at level M0. I mean, our ecosystem, our partners are at level M0. It's all implementation defined. With level M1, we want to kind of go with the BMC management services interface. That is the interface to the BMC. We plan to support both Redfish as well as IPMI. The host interface itself, there should be, there should be IPMI-based SSIF and Redfish host interface. Currently, IPMI-based host interface, we can't use KCS or BT or any other LPC mechanism, because the ARM-based SOC host doesn't have any of those interfaces. So SSIF is kind of the one which we can use for now. So rest of the interfaces are implementation defined at this point for level M1. For level M2, we kind of have a SOC to BMC interface. It says implementation defined here, but we kind of plan to use MCTP or SMBus as an interface between the service management controller and the BMC. For the BMC to platform elements, basically to different sensors on the board are connected to this SOC. We plan to use Redfish, PLDM, MCTP. And for the BMC management services interface, it's the same as level M1, which is either Redfish as well as IPMI. Host interface is same as level M1. And for BMC to IO device, we plan to have follow the NCSI specification, which is based off of DMTF forum. So we kind of want to accelerate the development of the specification. So with that intention in mind, 3 different sub-teams were formed. One was in conjunction with our partners. One was the reliability, availability, serviceability team, basically the RAS. Then the other one was the platform monitoring and control team. And the third one was the remote debug team. So these are the features which we plan to kind of present a design proposal soon to the OpenBMC. So RAS subteam is basically concentrating on creating an interface requirements for RAS errors. We plan to leverage common platform error records or CPER records, which are defined in UEFI specification. One of the key requirements there is we cannot use system event log because it's just 16 bytes long, and the requirement is to kind of have more information in the log so that it's useful for the administrator to debug any of the RAS errors. As well as one of the goals of this subteam is to inject RAS hardware errors. So I guess the figure isn't visible, but I can explain it. So basically the RAS errors in our ARM architecture, it's kind of generated once it's generated in the application processor. It kind of can create a CPER error record on the, there are 2 different approaches to handle RAS events. One is called the firmware first approach, and the other is the kernel first approach. In the firmware first approach, it's the RAS error events are kind of given to what we call as a system satellite management controller or a service management controller. This is system implementation defined. Since ARM doesn't manufacture systems, our specification should cater to different system implementations. So the satellite management controller, almost all of our partners do have that. So there needs to be a mechanism to transfer CPER error records to the BMC. So the CPER error records are kind of huge. It is in the order of kilobytes. So when the satellite management controller receives the CPER error, it kind of invokes this is the M2 compliant MCTP interface, which I'm describing. For IPMI, it's the flow is a little bit different. So what happens is it will invoke event message supported API to the BMC. This event message supported is part of the PLDM spec. And the BMC will return the list of event classes that it supports. So the satellite management controller, based on the list of event classes that are supported, kind of determines, yes, the RAS event is supported. Let me send the size of the error record to the BMC. So next, it invokes the platform event message, event message buffer size, which is a standard API, which is defined in PLDM for platform and monitoring specification. This BMC checks for the CPER size and returns back the maximum communication buffer size that is supported for the payload. Then the satellite management controller kind of determines whether CPER exceeds the max buffer size. If it is, then it needs to do a multi-part transfer. So for doing a multi-part transfer using PLDM, there is a standard API, which is platform event message, which kind of sends the, we don't have this event class yet. This is called, which we are defining. This is RAS poll event, which we kind of plan to propose it to the DMTF to add it in their PLDM for monitoring and control specification. So this RAS poll event, when it goes to the BMC, BMC realizes that it's a multi-part transfer, and it acknowledges the RAS poll event. Then it kind of calls poll for platform event message. BMC calls poll for platform event message, which with get first part as the parameter. And the satellite management controller kind of returns, here is the data for the first part of the message. And BMC keeps on invoking poll for platform event message using the data handle provided with the response from the satellite management controller. So finally, once the internal buffers of satellite management controller is empty, it kinds of sends end flag back to the BMC, and the BMC will kind of acknowledge that, saying, yes, I received the entire transmission. And the satellite management controller still can check its internal buffer. If everything has been transmitted, it will send back saying start and end, and returning the event ID as null. Okay, so the next subteam, which is basically to kind of monitor different sensors and control them. So for this, we support, there are different compliance levels which kind of supports IPMI, as well as we plan to support MCTP PLDM based mechanism to manage not just the numeric sensors, but as well as the state sensors like firmware, progress report codes, similar to post codes. So for this, the sequence diagram is pretty simple. We plan to use the platform descriptor concept, platform descriptor record concept, which is similar to SDR, which is an IPMI. This PDRs kind of provide the semantic information. So the flow kind of looks like, I'm just describing the MCTP PLDM flow, and IPMI, it is pretty standard, the same standard way which you guys have been using, will be using that. So what happens with PLDM is assuming that there is a PLDM terminus on the BMC and PLDM terminus on the satellite management controller. When the satellite management controller kind of boots, it will get its terminus ID and kind of let the BMC know that the terminus is ready to receive commands. And the BMC kind of invokes a standard PLDM command called get PDR repository info. This basically kind of queries the satellite management controller, give me the information about all the sensors which you kind of have. This is the use case where the sensors are connected to satellite management controller rather than on the board directly. So the BMC will run the run init agent. Run init agent is basically what it does is it looks for the initialization platform descriptor records. For example, numeric sensor effectors that are associated with the terminal. So for each PDR that is found, it sets the sensor type, sensor thresholds, hysteresis as directed by the PDR, the platform descriptor record, using the set sensor thresholds and the set sensor hysteresis command, which are part of PLDM for platform and monitoring specification. It may also enable event generation if the sensor supports it. And it may also set the default value like set numeric sensors. Once the BMC gets the PDRs from the satellite management controller, it kind of creates a central PDR repository, which has information about all the sensors that are kind of controlled by the satellite management controller. So whenever the BMC wants the reading on a particular sensor, it will invoke the get sensor reading by sending the sensor ID. Get sensor reading is also a standard PLDM API or a command. So the get sensor reading, the response of it would return a binary value, which is kind of in conjunction with the PDR. The actual value is calculated. That is, if X is the reading that it got from the sensor, and M is the resolution found in the PDR, and B is the offset in the PDR, then the formula is Y equal to M multiplied by X plus B. For example, if X is like BF and M is like minus, M is like 26.18 millivolt, and the offset is minus 1 volt. It roughly translates into plus or minus 4 volt. And the PDR also has additional information about the accuracy and the tolerance. So this is at a high level what we plan to do using PLDM and MCTP. So the other use case which we are currently kind of working on is the remote debug. This is basically to debug, source level debug the SOC using BMC as a some sort of a pipe where it kind of conveys the commands from the debugger with the debug server running on the BMC, and using the JTAG to kind of send that commands over to the SOC host and letting the user debug it. The other key objective of this is to ensure that only suitable debuggers can access the SOC. Not everyone can access the source level debugging. Okay, yeah, so this is how a remote debug from an ARM-based BMC to an ARM-based SOC looks like. We'll have at least the present proposal is to have an OpenOCD debug client. OpenOCD is an open source a debugger stack which has support for different ARM debug functions. It also has a ARM debug access port driver. So if the OpenOCD can run on BMC, and if it is provided with the SOC configuration, using a JTAG driver, which is hardware dependent, in theory, we can access the debug port on the SOC, and we'll be able to debug, source level debug the SOC. Okay, as I mentioned earlier, we plan to use OpenBMC as a medium to realize whatever features or specification requirements that we are adding to Server Base Manageability Guide. So ARM and ARM Silicon partners are participating in OpenBMC development at this point in time. So earlier, there was a lot of presentations from on PLDM. Probably we didn't have presentation on MCDP, but Deepak, I guess, and his team is developing PLDM for OpenBMC, as well. Jeremy from IBM is developing MCDP. So we plan to leverage their work and kind of have a use case for our RAS, which we discussed earlier. So if we translate that sequence diagram into OpenBMC design, it would look something like this. You would have a RAS daemon or a RAS app on the BMC side, which will link with libPLDM and libmctp. And on the host, on the SOC host side, we would have a libmctp, libPLDM libraries as well. Since it's written in C, I guess it's portable. And on the host side, we would have a RAS driver. So both of them kind of initializes the PLDM. It calls init API, which is provided by PLDM. It can either be blocking or a non-blocking. And MCTP should also get initialized by calling into MCTP init. And then there is an MCTP binding in it to specify the physical interface the MCTP should be bound to. And once that happens, it returns back to RAS app saying that, yes, I initialized the PLDM and MCTP endpoint and the PLDM terminus for you. And the same thing happens on the satellite management controller side as well. The RAS driver will have that status with it. So once RAS driver on the satellite management controller, if it either generates a CPER or receives the CPER, it kind of invokes encode PLDM command API, which I guess is part of libPLDM. And the parameters, I haven't shown all the parameters, but mapping that back to the PLDM sequence diagram, it's just, it would be the RAS poll event. And once the PLDM message is constructed, it can be sent using the send message API defined by the MCTP library. And it carries the payload across the physical layer. And the RAS app on the BMC side gets a notification if it has register for it. And once it gets the notification that it has got a request, it would generate a PLDM response and then send it back the same way using the send message API defined by the libmctp. And since this is a multi-part transfer, then there is a poll for platform event message that needs to be sent to get all the parts of the RAS error record. All right. So for platform monitoring and control, we don't have anything at this point, but we soon plan to have a design based on the PLDM sequence diagram, which we will be sending it to OpenBMC. But for remote debug, I guess I sent a proposal earlier in July, and we completed an internal demo, which is the first part where the GDB client would be running on the user administrator side, connecting to port 333 on the OpenOCD debug server. Next phase of implementation is to kind of utilize a wrapper which adds JTAG master core infrastructure. I guess we were looking at some of the patches which were present in OpenBMC. So we are pretty sure that we can reuse one of those, and we will provide our own hardware-specific driver to connect to this interface. All right. Okay, so this was a roadmap or a plan when we started. So this basically lists platform monitoring and control use case, and then remote firmware upgrade, which we haven't embarked yet. And then we have a BMC RAS errors implementation, which we are at a stage where we think we can contribute to OpenBMC on this. And the other use case was the remote debug capability. This also we are at a stage where we can contribute to OpenBMC. All right. So these are the list of things that would be beneficial in order to realize SPMG and an implementation based on SPMG. So we are participating in OpenBMC to enable reference implementation. And we are participating in OCP as well to influence hardware management specifications and design. We are participating in DMTF work groups. In case you guys are interested to be part of this specification, send an email to ARM and we can add you. All right, that's it I had. Thank you. Any questions I can take?
So do you have anything like a serial over LAN, or how do you see that host console from the BMC?
So basically the management port, it's the level M1 kind of supports IPMI serial over LAN implementation.
Hey, so I'm curious for the remote debug, were you able to do some performance profiling to see like what kind of performance do you get for this debug over network?
If you are talking about scaling, we are not yet at that stage where we can measure the performance.
Okay.
But
you have
with a single
okay.
host, it's seamless for the network.
So if I were to do like a set a breakpoint or a memory dump, this is something that can be completed relatively quickly. It will not.
Yeah, since it's a JTAG interface, it's just limited by the JTAG interface speed.
Oh, I see. So it doesn't require much cycle from BMC and the network side as well.
It would require some cycles from the BMC because the OpenOCD debug server is running on it.
Yeah,
but it just acts as a pipe, and the payload is very small.
Okay. So the main bottleneck is still JTAG.
Yeah.
Throughput. Okay, cool. Thanks.
Any other questions?
So I'm assuming all the sensors data and everything you will be expecting as a part of that PLDM packets from the host, whatever you expected.
One of the methods is the platform descriptor records. Other is the sensor STRs defined in IPM.
And is there anything you would be thinking of, a fan controller, or are you going to have in the design?
PWM tag.
Tag.
Yeah, so we kind of defer that to how the OCP specification specifies it.
So do you expect BMC to control the fan?
Yes.
Thanks.
Right. Thank you.